How modern RAG pipelines are solving the LLM hallucination problem. Introduction. Imagine asking an AI assistant a simple question about a court case, and it confidently gives you a detailed answer, complete with citations, quotes, and page numbers. The only problem? None of it is real. The case doesn't exist. The quotes were invented. This isn't a hypothetical. It's happened to lawyers, students, and businesses around the world, and it has a name: hallucination. For the last few years, hallucination has been the single biggest obstacle standing between large language models and real-world trust. You can't put a model into a hospital, a courtroom, or a financial system if it sometimes just makes things up with total confidence. But here's the good news. Over the past 2 years, a technique called Retrieval-Augmented Generation, RAG, has evolved from a simple trick into a sophisticated engineering discipline that is dramatically reducing hallucination rates. In this video, we're going to go deep into how modern RAG pipelines actually work, why they help, where they still fail, and what the cutting edge looks like right now. By the end of this video, you'll understand the full anatomy of a production-grade RAG system, from chunking and embeddings to hybrid retrieval, re-ranking, self-correction loops, and grounded generation. Let's get into it. Why do LLMs hallucinate? Before we can appreciate the solution, we need to understand the disease. Large language models are, at their core, next token predictors. During training, they read enormous amounts of text and learn statistical patterns about which word is likely to follow another, given the context so far. There's no internal database of verified facts sitting inside the model. There's no lookup table. Everything the model knows is compressed into billions of numerical weights, and when you ask it a question, it's essentially performing an extremely sophisticated form of pattern completion. This creates 3 distinct failure modes. The first is what researchers call parametric knowledge gaps. If a fact wasn't well represented in training data, or if it happened after the model's training cutoff, the model has no reliable way to know that it doesn't know. It will often still generate a fluent, confident-sounding answer, because fluency is what it was trained to produce, not necessarily truthfulness. The second failure mode is what's sometimes called exposure bias, or more informally, the model's tendency to prioritize plausible-sounding continuations over factually verified ones. Since training rewards the model for producing text that resembles its training distribution, a well-formed but false sentence can score just as well internally as a well-formed true one. The third mode is context drift in long conversations, where the model gradually loses track of what's actually been established versus what it's inferring, and starts blending the two together. Now here's the key insight that makes RAG so powerful. A huge portion of hallucination isn't a reasoning failure. It's a knowledge access failure. The model isn't being irrational, it simply doesn't have the right facts in front of it, so it fills the gap using its general priors. If you could somehow hand the model the exact right passage of text right before it answers, a huge fraction of these hallucinations simply disappear. That single insight is the entire foundation of Retrieval-Augmented Generation. The core idea of RAG. At its simplest, RAG works in 2 stages: retrieve, then generate. Before the language model writes a single word of its answer, a separate retrieval system searches through an external knowledge source. This could be a company's internal documents, a medical database, Wikipedia, or the live web, and pulls out the passages most relevant to the user's question. Those passages are then inserted into the model's prompt, essentially saying, Here is some trustworthy, up-to-date information. Use this to answer the question. This sounds simple, but the engineering underneath it is where the real progress has happened. The first challenge is, how do you search over millions or billions of documents fast enough to be useful? The classic solution is to convert text into embeddings, long lists of numbers that represent the meaning of a piece of text in a high-dimensional space. Two pieces of text that mean similar things end up as vectors that are close together in that space, even if they don't share any of the same words. Once documents are embedded, they're stored in what's called a vector database. When a user asks a question, that question is also converted into an embedding, and the system searches for the document vectors that are closest to the question's vector, typically using a similarity measure like cosine similarity. The idea behind that formula is straightforward, even though the math looks intimidating. It measures the angle between two vectors, and vectors pointing in nearly the same direction get a high similarity score, regardless of their length. This retrieval step transforms the LLM from a closed-book exam taker into an open-book one. Instead of relying purely on memorized, potentially stale, potentially fuzzy knowledge, the model gets to read the relevant material right before answering, dramatically increasing the odds that its answer is grounded in something real. But, and this is important, early RAG systems from a few years ago were fairly naive. They chunked documents into arbitrary fixed-size blocks, retrieved the top few matches, and stuffed them into the prompt. That basic approach helped, but it still hallucinated plenty because retrieval itself can fail in subtle ways. The rest of this video is about how modern pipelines fix those subtle failures. Smarter chunking and indexing. One of the most underrated fixes in modern RAG pipelines is simply getting smarter about how documents are broken into pieces, or chunks, before they're indexed. Early systems just split text every few hundred words, regardless of whether that cut a sentence, a table, or an idea in half. If a chunk boundary lands in the middle of an important explanation, the retrieval system might only grab half the story, and the model, trying to be helpful, fills in the missing half with a guess. That guess is a hallucination in disguise. Modern pipelines use what's called semantic chunking, where the text is split at natural boundaries, the end of a paragraph, a section header, or a shift in topic, often detected by measuring how much the meaning changes from one sentence to the next. Some systems go further with hierarchical indexing, where you don't just index small chunks, but also index summaries of larger sections, and summaries of summaries above that. This lets the retrieval system zoom in or out, similar to how a human might first find the right chapter of a book, then the right paragraph. Another major improvement is metadata-aware retrieval. Instead of treating every chunk as anonymous text, modern systems attach metadata: the source document, the publication date, the author, the section title, and use that metadata to filter and re-rank results. This matters enormously for avoiding a specific type of hallucination: outdated information being presented as current. If a system can filter to only documents published in the last 6 months, it avoids confidently citing a policy that was replaced last year. Finally, there's the idea of contextual chunk embeddings, a technique where, instead of embedding a chunk in isolation, the system embeds it together with a short summary of the whole document it came from. This solves a subtle but common problem. A chunk that says, "The interest rate was reduced by 0.5% is meaningless on its own. Reduced from what, by whom, when? Contextual embedding bakes in just enough surrounding information so the retrieval system understands what the chunk is really about, even out of context. dense, sparse, and hybrid retrieval. There's a second major axis of improvement: how the actual matching between a question and a document happens. Pure embedding-based search, often called dense retrieval, is excellent at understanding meaning and paraphrase. If you ask about a car that runs without gasoline, it can find documents about electric vehicles even though the words don't overlap. But dense retrieval has a weakness. It can struggle with very specific, rare terms, product codes, legal statute numbers, exact names, because those specific tokens can get diluted in a dense vector representation. That's where sparse retrieval comes back in. Older algorithms like BM25, which score documents based on exact keyword overlap and term frequency, are still extremely good at pinpointing exact matches. The idea behind these scoring formulas is that a term which appears frequently in a specific document, but rarely across the whole collection, is a strong signal that this document is highly relevant to a query containing that term. Modern RAG pipelines don't choose one or the other. They combine both in what's called hybrid retrieval. The system runs a dense semantic search and a sparse keyword search in parallel, then merges the two ranked lists using a fusion method, one popular approach being reciprocal rank fusion, where each document gets a score based on how high it ranked in each individual list, and documents that rank well in both lists rise to the top. This hybrid approach captures the best of both worlds: the conceptual understanding of dense vectors and the precision of exact keyword matching. This matters directly for hallucination because a huge class of factual errors comes from retrieval simply missing the right document, not because the generation model reasoned poorly, but because the search step never found the needle in the haystack in the first place. If the right passage never makes it into the prompt, no amount of clever prompting will save you. Improving retrieval quality is, in a very real sense, improving truthfulness at the source. Reranking and context curation. Retrieval gets you a shortlist of candidate documents, but not all of them are equally useful, and cramming too many into the prompt creates its own problems. This is where re-ranking comes in, a second, more computationally expensive but more accurate model that takes the initial candidates and rescores them by actually reading the query and each candidate together, rather than comparing pre-computed vectors. These are often called cross-encoders because the query and document are encoded jointly, letting the model directly compare fine-grained details rather than relying on a rough geometric distance. Why does this matter for hallucination? Because there's a well-documented phenomenon called lost in the middle. Research has shown that language models pay the most attention to information placed at the very beginning or the very end of their context window, and tend to underweight information buried in the middle, even when that middle information is highly relevant. If your retrieval system dumps 10 mediocre passages into the prompt, with the one truly relevant passage buried at position 6, the model may effectively fail to use it and hallucinate an answer instead. Modern pipelines address this with careful context curation, re-ranking to promote the most relevant passages, deduplication to remove near-identical redundant chunks, and deliberate placement strategies that put the most important information at the positions the model attends to most. Some systems also implement a relevance threshold. If the top retrieved documents all score below a certain confidence level, the system doesn't force-feed them to the model at all. Instead, it triggers a fallback response acknowledging that no sufficiently relevant information was found. This single design choice, being willing to say, "I don't have enough information," is one of the most powerful hallucination reduction techniques there is, because it directly targets the model's tendency to always attempt a fluent answer regardless of whether it actually has the goods. Self-correcting and agentic RAG. The most exciting frontier in RAG right now isn't just about retrieving better. It's about giving the system the ability to critique and correct itself before the answer ever reaches the user. This family of techniques is often called self-RAG or corrective RAG, and it works a bit like giving the model an internal editor. Here's how it works conceptually. After the initial retrieval, instead of immediately generating a final answer, the system generates a draft answer along with an internal judgment. Does this retrieved context actually support this claim? If the system detects that a retrieved passage is irrelevant or that its own draft answer includes a claim not backed by any passage, it doesn't just ship that answer. It can trigger one of several corrective actions. Retrieve again with a reformulated query. Search a different knowledge source entirely, including, in some architectures, falling back to a live web search if the internal database comes up empty, or simply strip out the unsupported claim before finalizing the response. This turns RAG from a single-pass pipeline into an iterative loop, sometimes visualized as retrieve, generate, critique, and, if necessary, retrieve again. Some of the most advanced systems now use what's called Agentic RAG, where the language model itself acts as an orchestrator, deciding in real time which knowledge sources to query, how many retrieval rounds are needed, and when it has gathered sufficient evidence to answer confidently. This is a meaningful shift. Instead of a fixed pipeline designer deciding in advance exactly how retrieval will happen, the model plans its own investigation, much like a researcher deciding to check just one more source before writing a conclusion. The hallucination reduction impact here is significant because it adds a verification layer that specifically targets the moment where hallucination is born, the instant the model is about to state something it isn't actually sure about. Instead of that uncertainty silently becoming a confident-sounding sentence, the system has a built-in checkpoint asking, is this actually grounded? Grounding, citations, and verification layers. The final piece of the puzzle is making the model's reasoning visible and checkable rather than a black box. Modern RAG systems increasingly require the model to attribute every factual claim to a specific retrieved passage, essentially forcing inline citations as part of the generation process itself, not bolted on afterward. This has a subtle but powerful side effect. A model that has to point to exactly which passage supports a sentence is far less likely to write an unsupported sentence in the first place, because the citation requirement acts as a constant, built-in self-check during generation. On top of that, many production systems now add a dedicated post-generation verification step. After the answer is drafted, a separate checking pass, sometimes another LLM call, sometimes a specialized classifier, compares each sentence in the answer against the retrieved passages and flags any statement that isn't actually supported. Think of it as a fact-checking desk that reviews the article before it's published. If unsupported claims are found, the system can either delete them, rephrase them as explicitly uncertain, or trigger another retrieval round. Together, these grounding techniques close the loop. Retrieval finds the facts, chunking and hybrid search make sure the right facts are found, re-ranking makes sure they're prioritized correctly. Agentic self-correction catches gaps in real time, and citation-based verification acts as the final safety net before the answer reaches the user. No single layer is perfect on its own, but stacked together, they've moved RAG systems from helpful but unreliable to something increasingly close to genuinely trustworthy for high-stakes use cases. Limitations, open challenges, and closing. Now, it's worth being honest. RAG is not a silver bullet. Retrieval can still fail if the underlying knowledge base is incomplete, biased, or itself contains errors. Garbage in, garbage out still applies. Multi-hop questions, where the answer requires combining facts from several different documents in a chain of reasoning, remain genuinely difficult because a single retrieval pass might miss one crucial link in that chain. And there's an ongoing tension between adding more verification layers and keeping response times fast enough for a good user experience. Every extra check adds latency. But the trajectory is unmistakable. What started as just paste some search results into the prompt has evolved into a genuinely sophisticated discipline, combining information retrieval, self-critique, and structured verification. The systems we've walked through today, semantic chunking, hybrid dense sparse search, cross-encoder re-ranking, self-correcting agentic loops, and citation-based grounding, represent the current state of the art in making language models not just fluent, but actually trustworthy. If you found this breakdown useful, consider subscribing for more deep dives into how modern AI systems really work under the hood. And let me know in the comments, have you run into an AI hallucination in the wild? I'd love to hear your story. Thanks for watching, and I'll see you in the next one.